we're going to look at some probability today. So looking at this bar graph, it's a probability distribution like you had in geometry. So each bar represents the probability that your variable has those values. We want the probability x is 2 or 3. So let's look at them one at a time. The probability x is 2 is, it looks like approximately equal to, I'm going to say that's 0.24 if you look at the height of that bar. If you look at the probability that x is equal to 3, that looks right about 0.25. So if you want the probability that x is either of those numbers, 2 or 3, then you just add the two probabilities together, and 0.24 plus 0.25 would get you about a 49% probability that x is either 2 or 3. You can do decimal, you can do percents when you're talking probabilities, it doesn't matter. So if you look at what's called a normal probability distribution, the probability distribution is going to be like a symmetric bell-shaped curve. So like tallest bar in the middle, and then it's going to have less probability that you have higher or lower values. And it's actually for what's called a continuous probability distribution. So your data value could have any value, not just like x is 2 or 3, it could be like 2.567. The nice thing about normal distributions is there's a lot of like naturally occurring data that's got that normal distribution shape, like heights, weights, IQ scores. So if you know some properties about normal distributions, you can learn a lot about data value that's normally distributed, including like probabilities. So you've got your distributions between like what percentage of data values fall within each range. So you can calculate your probabilities for any data that's a normal distribution. If that looked like gibberish, don't worry, but we'll do one. It's no big deal. Okay, so I've got scores on a math test that have a bell-shaped or normal distribution. The mean is 75, so that goes in the middle. And then my standard deviation is 10, so if I'm getting bigger as I go towards the right, I'll be adding 10 to get kind of my boundaries between the number of standard deviations. And if I go smaller, I'm going to subtract my standard deviation of 10. And then since this is a bell-shaped normal distribution, the percentage of data values that fall in between like 65 and 75 or 75 and 85 are going to match those on my normal distribution. So like if I am within like one standard deviation, that's a 34% probability that I get a test score that falls in each of those ranges. If I go out further away from my mean, so within 2 standard deviations, it's 13.5% probability I'm in that range or that range. And then 3 standard deviations out is a 2.35% probability. So your probabilities are getting smaller as you go outwards from your mean, because most of your data values or test scores are going to fall in the middle there. And then 4 standard deviations away is just barely can even see it on my distribution there, 0.15% of my data values. Okay, so now that it's all labeled up, I can answer things about probabilities and percentages. We want the percentage of test scores between 75 and 95. So that is within that range right there. So if it's between 75 or 85, that's a 34% probability. 85 to 95 is 13.5. So the probability it's one or the other, in between that range anywhere, is, add them up, 47.5% chance that you'll have a test score that falls within that range. Yes, it just says 79.5 now. Ignore that. I fixed it. So the probability my test scores are between 65 and 85, if I grab one at random, is 34% plus 34%, 68% chance it's in between 65 and 85. So we've got a student who takes a random sample of students from his high school and asks how much they usually spend on fast food each week. So we got a mean of $6.50, standard deviation of $1.75. We want to know how many students at the school spend between $8.25 and $10 each week. And this data is a normal distribution. So let's label. So mean of $6.50, adding our standard deviation of $1.75, and labeling. I'm actually going to just go up and copy my percentages that I wrote earlier, because this is still a normal distribution, so my percentage of data value should be the same. between each standard deviation. So if I make it to scale, because my picture's not exactly perfect here, and there we go. Okay, so what I want to know is approximately how many students spend between $8.25 and $10 on fast food each week. So $8.25 to $10, 13.5% of my students spend that amount. That's not the number of students at the school who spend that amount. That's 13.5% of my 2,850 students. So to answer the question, I need to actually take 13.5% times 2,580 students, which will give you 348.3 students, but you can't have like 0.3 of a student. So just round. 348 students it is. One thing that is kind of useful to know is whether or not your data set actually falls in the shape of a normal distribution or not. So we're going to take this data set and compare. So if my mean of my 15 numbers that I've got up there is 4.64, and my standard deviation is 2.85, if this was a normal distribution, and I added my standard deviation and then subtracted it and broke it into those ranges, I should get the percentage of data values that fall within those ranges to match my normal distribution that I've got down below. So I'm going to calculate those percentages and see if they're close or not. So what percentage of this data set is within one standard deviation of my mean? So that's either one standard deviation below or above, so between 1.79 and 7.49. Those numbers highlighted in green fall in that range. If you count them up, that is 10 out of my 15 data values, which is 2/3 of them, or approximately 67%. If you compare that to a true normal distribution, 34 plus 34, 68% of the data values in a true normal distribution fall within one standard deviation. So that's actually pretty darn close. Checking within two standard deviations of the mean, we're between negative 1.06 and 10.34, so that contains all of my data values except 12. So 14 out of my 15 data values are within two standard deviations of my mean, which is approximately 93%, compared to, if you look within two standard deviations of a true normal distribution, can add them all up, or you could scroll to the top and it's there. It's 95%. So again, still not too far off. If we go three standard deviations, I didn't actually label those numerical boundary lines on my distribution, but if I add another 2.85 to 10.34, it's going to have 12, my last data value, within there. So 100% of my data values in my data set fall within three standard deviations of the mean, which is 99.7%. So if you actually want to not add all those up, it's the percentages that are up here. You can use that. So if I want to decide if this is an approximately normal distribution or not, let's see how close it is. So comparing those two, there's a 1% difference. Comparing those two, there's a 2% difference. And comparing within three standard deviations, it's a 0.3% difference. I would say anything within 5% is small enough to call it approximately normal, and this is very close to an approximately normal distribution. The biggest difference I have is 2%.